And please, it's now time to go to the next talk today, given by Tiago Badaro Saramela from University of Sao Paulo. And the title of talk is Aging of Micro-Patterned Gaseous Radiation Detectors Analyzed by ToF-SIMS. Please, Tiago, are you online? Yes. Good. Please
You're going to need to unmute, yeah? You're on mute. Bottom left of your screen.
Oh, sorry about that.
Tiago, we can hear you.
You're hearing me?
Yeah, can now. Okay. Now we can't. I think you may have a bad connection somewhere. With your microphone, maybe? Are you using a...
My microphone.
Yeah, it was okay for a minute there and then it disappeared again.
It is turning down the volume automatically.
Okay, it's okay now, yeah.
Okay, I think I will talk a little.
Yeah, just stay where you are. That's probably... Don't move.
If you lose me again, please let me know. Okay, thank you for the introduction, Primers. And
we've lost you.
Lost you? You lost me again?
It's okay, I think you weren't speaking. It's okay.
Okay, sorry, my presentation don't want to start. Oh, then. Okay. Are you seeing me, the presentation in full?
Yes, that's nice.
Oh, thank you. Sorry again by the delay. So I'm presenting you, this work is a collaboration between the University of São Paulo in Brazil and the University of Nottingham. And we aim here to use ToF-SIMS to analyze the positions that happen in micro-patterns gaseous detectors. And with this, we want to understand what the source of those depositions. And it's also a part of a work done to support the increase of luminosity of LHC. In this case, the upgrade is in Alice, one of the experiments at LHC, and in one of its detectors, the TPC, that you can see here in red, the detectors using are transitions from multi-wire proportional chambers to GEMs, the gas electrodes multipliers. And to talk to you about the TPC, it's more or less the heart of the experiment. It's responsible to producing the tracks of the particles. And it's so important that it's even in the logo of the Alice experiment, as you can see in the top left. So these are the GEMs, the detectors that we are analyzing. It's a thin foil of Kapton with copper in both sides. Those foils are perforated and a voltage difference is applied between these copper layers in such a way that a high electric field is produced inside of those holes. The objective of these foils is to multiply the electrons come from the particles that cross the TPC. That's a huge cylinder filled with gas. And you can see at the bottom where these detectors are placed at the end caps of the TPC. Okay. And I'm showing here an animation of the workings of these GEM detectors. And here we are seeing the primary electrons produced by the charged particles. And as they come inside of the holes, the avalanche process starts that produce the multiplication of the charges. But this avalanche produces also a cloud of positive ions that you see here in red. Most of well, most of those positive charge particles collide at the top surface of the detector and are neutralized. And if for some reason some of those positive charges are complex molecules that can be attached to the surface and create deposits on them. And this deposit can be problematic and cause damage to the detector. And why so? Because of something called the melted effect. The thing is, if we have a copper surface and on top of it we have an insulating layer, this will decrease the neutralization rate of those positive ions. If the positive charge induced by this process is high enough, this can emit electrons that was originally inside of the metals, and these electrons will be available in the gas and will produce an avalanche and a multiplication process. And what will happen is a positive feedback loops the avalanche produced by the emitted particles will increase the positive charge, and this avalanche will happen continuously and in greater volume. And if this process is not stopped, this the outcome can be a discharge that can damage the device. Okay. So a conventional way of analyzing these deposits is by means of EDS and the measurement of elemental composition, as you can see in this plot in the right. But the problem here is that we can see that there is carbon, oxygen, and silicon deposited in the top of the copper, but without any molecular information. And without this information, we can't understand what the source of those deposits, and we can try to find out how to stop and mitigate those effects, right? So to try to resolve this ambiguity, we are now using ToF-SIMS to analyze those surfaces. The measurements that I will show here was done by our colleagues at the University of Nottingham in their ToF-SIMS equipments. And the sample that we used was this file right here. It was a file using in a readout optical readout. One that readout is actually a camera that records when the avalanche happens, and the gas mixture was argon and CF4. This is important because we will see the fluorine in the analysis. And it was used until I spark killed it, as you can see here. Okay. And the first nice thing about ToF-SIMS that we can use it to create this depth profile, as I'm showing here. So in the surface plot, the ones with blue peaks here, we see the very top surface of this depth profile. This is the spectra of the first layers of our sample, and you can see there's a huge amount of peaks here, showing us that a lot of different materials deposited in this degraded detector. And at the bottom, we are seeing the most deep profile that we did, that is basically pure copper. So we are seeing the difference between a pure copper sample and the dirt surface that we end up after the degradation process that those detectors undergo. Okay. And other very interesting thing about ToF-SIMS is to combine the depth profile to 2D scans, as you can see here. And for this case, we saw that these organic fragments that you can see here, with the depth profile, we can see that after some depth, the signal vanishes, showing us that we are really see a very thin layer of organic deposits on top of this copper. Okay, and using And so what we are trying to do here is combine the information of the molecular fragments that you see with ToF-SIMS and the 2D patterns of the deposits to understand the origin of it. Okay, and and here I'm showing you three categories of those signals. First, copper and its oxide that are distributed everywhere, as of course in the surface. Second, we have this surface contamination, and the first one, the C3H4, is adventitious carbons that happens to be formed when the detector is exposed to air. In the middle, I think it's a very funny thing. It's actually a fingerprint, actual fingerprint from a finger. Someone poke the finger in this sample, and you see the signal of sodium that came from the sweat on the finger of this individual. And these are contamination done by exposure of in the ambient or the handling, and not inherent to the running the process of running the detector. Okay, in the last row we saw it's the organic patterns that is indeed produced during the functioning of the detector, and you can say so because of the patterns of this deposition that match the patterns of the deposition that I showed you earlier in that simulation, right? And also the composition of those the fragments, like the fluorine that was contained in the gas mixtures used here, and also the nitrogen here, that it's a component of the capstone itself that makes up those files. And I want to take a closer look at this fragment because there is a very interesting story about this. This is a very complex and molecule that we are not expecting to see it, and it's what we found out. It's a signature of degraded capton, and we see that by looking at the peak of this specific fragment here. In orange, we have the degraded gem spectra that I'm showing here, and in blue down there we have a pristine gem that was never used, and we can see that this peak it's not present there. Okay. In green, okay. In green we see a pristine capton, so there's a little peak, but not a pure capton, no copper here. And in red, we have an argon irradiated capton. So what we conclude from this is that this molecule is indeed a signature of irradiated, a degraded capton that is on top of the copper. And if we look closer to the spark that killed the detector, we see a huge peak of this same fragment. So what we understand by that is that by some process, maybe the avalanche or maybe micro discharge, there is a removal of capton inside of the holes. This fragment of capton is attached to the surface of the detector, and with the melted effect, this can induce discharge that can damage the detector, and it's again a positive feedback loop, because at every new micro discharge, this deposition will increase and also increase the power of the discharge by the melted effect. And just to summarize, we are using ToF-SIMS to give us this whole new dimension to understand not that there is deposition, but what the source of it. And with the knowledge of what is the source, we can try to understand how to mitigate and prevent this from happening. One drawback is that we have a blind sample, we don't know its history, and now we're building a apparatus to make a dedicated experiment to age in a controlled manner, so we can go further in this analysis. Okay. So this concludes my presentation. Thank you very much for your time and attention.
Thank you, Tiago. Now time for some questions. Any question from the audience? Okay, I would just ask if there is any alternative to Kapton. We all know that this is extremely tough polymer.
Yes.
And even in this case, you got some, I would say, sputtering deposition there. Did you think on some alternatives, or difficult to find?
I think the great advantage of Kapton is the ease of handle, right? It's easy to manufacture. For large versions of this kind of detector, there are ones like with this one is very thin, like 50 microns. For large versions, you can go more wide. There are some people that use glass actually, but for thinner versions, and for such larger surface like those using at LHC, at the LS, like with 1 meter a meter squared of area, I don't know how feasible it will be to manufacture such large foils. No.
Okay. Thank you, Tiago. It's time to go to the next talk. Thanks for nice and interesting presentation.